Okay, awesome. Okay, so right, yeah, maybe just an overview. So I'm going to be talking about some phases of matter that we're calling Bose Luttinger liquids, and yeah, I think the topic that we're going to be talking about today is kind of like a little bit not so mainstream, but I think maybe the general and maybe not so close to experiment, but I think the general ideas are kind of interesting. And certainly if you're interested in like field theory things or non-Fermi liquids, this kind of stuff, then it might be of interest. So yeah, anyway, hopefully we can have some fun. So um, I just have a few like introductory motivation slides here. And yeah, so because I got into condensed matter physics from reading Xiaogang Wen's book, I have to start talking about like classification of phases of matter, right? So yeah, so basically, if you want to think about all the different kinds of phases of matter that a condensed matter person would want to be dealing with and want to classify it, you can kind of group phases of matter into a few different classes based on sort of how complicated they are in the IR at low energy. So of course, the simplest types of phases to deal with from this perspective are phases where you only have a finite number of degrees of freedom in the IR. So these theory, you could have 0 degrees of freedom and you just have a trivial gap theory, or you could have some like finite number of ground states. And yeah, so this basically situations where things where you're in a situation like this are usually described by topological quantum field theories. And we have a huge mathematical kind of toolkit to understand what goes on in these kind of scenarios. Lots of progress has been made, kind of feel like we understand these things very well. That's if you have almost no degrees of freedom in the ground state. If you have more degrees of freedom, say you have a system where the gap closes at some finite number of points in momentum space, then the low energy physics of a phase like this would usually be described by some sort of quantum field theory. And so we have a gap closing at a few points, and then we usually just study excitations about those points. And we use this whole powerful framework of quantum field theory. Often we can do even more, and we can use stuff from CFT to make stronger statements about how the way these phases behave and blah, blah, blah. And, of course, CFT is harder than topological field theory, but it still has there's still lots of powerful tools that we can use to make progress on understanding how an organizing principle for these kind of phases. Okay, but then there's another kind of more complicated phase of matter, which is something where you have like a lot of low energy degrees of freedom, more than just like an isolated number of modes of gap closings in momentum space. These are, I think, John McGreevy calls these very gapless phases of matter, which I like, and it's the terminology I will use. Of course, the canonical example of a phase of matter like this for condensed matter physics is a Fermi liquid, right? So a Fermi liquid, you have a gap. You have the low energy degrees of freedom in a Fermi liquid are located at a non-trivial submanifold of dimension greater than 0 in momentum space. And this is not going to be really described by a conventional quantum field theory, sort of, because you have many more low energy degrees of freedom. And since we don't really have taking this very like high level classification of phases of matter kind of perspective on a problem like this, we don't really have any super concrete expectations for the kind of general properties that phases of matter with a lot of gapless degrees of freedom like this should satisfy, right? So what this talk is going to be about is it's going to be about a kind of a new example of one of these kind of very gapless phases of matter, which is not a Fermi liquid, and it's not really like everything that's not a Fermi liquid is a non-Fermi liquid, but it's also not like something that is kind of close. It's not made of fermions, and it's not like obtained from a Fermi liquid by adding some extra stuff, but in some sense it's like a Fermi liquid, and it gives us a kind of a new example of very gapless phases of matter that we can kind of use to build some better expectations for what we expect these phases of matter to satisfy. Okay, yeah, and so in particular, we're for the rest of the talk, we're only going to be working in bosonic systems. So we're not going to be able to create a large amount of gaplessness by using degeneracy pressure as you would in a Fermi liquid. Okay, so that's the preview and kind of motivation. And in order to kind of like get warmed up, I'm just going to kind of describe the one way to think about Fermi liquids, because what we're going to be doing with these Bose-Luttinger liquid things is going to come from sort of a similar philosophical standpoint. So one way to think about a Fermi liquid is essentially to think about of the Fermi gas as a bunch of kind of chiral or one-dimensional Dirac fermions that live in momentum space. So what you do here is you take the dispersion and you linearize it about the Fermi surface, right? And when you do this, of course, the dispersion is going to be just some VF times K linear dispersion at the Fermi surface. And then the picture that you have of what the Fermi liquid looks like is what I've kind of sketched here. Each one of these, so the circle here is a Fermi surface in 2 dimensions, and each one of these little lines you're supposed to imagine as being this fermion, this kind of chiral fermion that lives, disperses in 1 + 1 dimensions, and you're supposed to think of essentially having one of these chiral fermions for each sort of location on the Fermi surface. Right? And this sounds a lot more complicated. A description in terms of an infinite number of chiral fermions like this sounds more complicated than just thinking of, it's a Fermi gas. I just fill boxes in momentum space until I filled up to the chemical potential, right? But this kind of IR focused, IR centric perspective will be useful when we try to think about other kinds of more exotic examples of phases like this. So okay, yeah. So why is this perspective in terms of an infinite number of fermions at each point on the Fermi surface useful? It's useful because it allows you to address questions like, is the Fermi liquid, the phase of the Fermi liquid, is that stable to adding perturbations to the free fermion Hamiltonia? Yeah, so this is where this kind of description really becomes useful. And what goes on here is, so for example, let's just address this question of, is the Fermi liquid stable with respect to adding interactions between the fermions? And this is a very well-known story, right? What happens is let's add some general kind of 4 fermion interaction here that I've written, and let's examine whether or not this 4 fermion interaction is relevant in the renormalization group sense. And okay, the exact way you determine whether or not this is relevant is not super important for the present discussion, but the result is that you find that this BCS pairing for superconductivity is either marginally relevant or irrelevant depending on the sign of the coupling. That's the first bullet point. Then you find that forward scattering processes where it's just like the number density sort of interaction at 2 points on the Fermi surface, not scattering fermions around at different points on the Fermi surface. You find that these kinds of interactions are marginal, and everything else, all the other possible interactions of this 4 fermion type that you can adding, are all irrelevant. And so, yeah, and so that's kind of the utility of decomposing the Fermi surface into a bunch of different Dirac fermions like this. It allows you to perform calculations that lead to these results. And one interesting thing about the consequences of the relevance or irrelevance of these interactions is that you have what could be loosely called a U1 infinity symmetry, which emerges in the IR. So what this means is that in the IR, at least if we turn off this BCS interaction, you have the fermion number at each point on the Fermi surface is conserved, because terms which break that conservation are irrelevant under RG. Yeah, and so you have this gigantic symmetry group in the IR, which is kind of unlike, this is having a huge emergent symmetry group like this in a system that has, you can turn on irrelevant interactions and all that stuff. Having a huge symmetry group like this is kind of unusual, and yeah. So in what follows, the phases that we're going to be considering, these Bose-Luttinger liquid things, are going to be somewhat similar in the sense that they're also going to have a very large emergent symmetry group, and we're going to be using sort of a kind of similar framework to approach the problems that we're going to be studying in the following. Yeah, so here's a preview of what we're going to do. As I said, we're going to be interested in bosonic systems, and we're going to approach things as we would approach a Fermi liquid. So we're going to be considering bosonic systems that exist in the continuum, and for simplicity, we're going to have rotation variants, and like you would do like Landau did when he was studying Fermi liquids. Also, like this kind of more modern understanding of Fermi liquids that I was describing, we're going to try to use some understanding from 1+1 dimensional quantum field theory. In the Fermi liquid example, this was these chiral fermions living at each point of the Fermi surface. We're going to try to use some knowledge of 1+1 dimensional quantum field theory to build some bosonic phases that look like Fermi liquids. And the bosonic phases that we're going to construct, yeah, they're interesting. So we'll see that they don't have quasi-particles. They have lots of their renormalization group flows are very interesting, and in some sense they have Fermi liquid phenomenology. In some sense they don't, and yeah, etc. Any questions before I start talking about the new stuff, or should I just go on? Okay, I hope people followed the motivation here. So here's what we're going to be doing in the rest of the talk. So we're going to consider a system of bosons, and we're going to consider a system of bosons whose dispersion has a degenerate minima along some non-trivial manifold in momentum space. So here we're gonna just for simplicity choose this manifold to be a sphere. So we're going to consider systems where the dispersion looks like this plot at the top right. Now, the reason why we're going to do this is sort of obvious, right? I told you we're trying to build examples of phases where you have a lot of low energy degrees of freedom, right? And so, just like in a Fermi liquid, if we just kind of if we make a bosonic system that has low energy modes living along some non-trivial manifold in momentum space, then there we go. Then we have an example of a system that has lots of low energy degrees of freedom, right? So here, since we have bosons, we don't have a Fermi C and we don't have degeneracy pressure, but we can kind of just build in a Bose surface, if you like to call it, in the dispersion in this way. Of course, it's not really a surface because there's no really, like, we're not like filling any kind of Bose C, but we're just gonna work with a dispersion like this. Yeah, and so systems with a dispersion like this may seem sort of bizarre or weird, because normally we just consider systems that disperse maybe linearly or quadratically about some fixed point. But of course, examples of systems that have dispersion relations like this exist, right? So there's the famous Roton mode in helium. You have a dispersion where the minimum at non-zero momentum. Also, there are some superconductors that pair at finite momentum and would be described by things like this. There are also some magnets in which spin waves have this excitation. This happens in neutron stars apparently, and there are a lot of examples. Anyway, so we're not really gonna, for most of the talk, we're not going to be thinking about a specific concrete physical system. We're just going to suppose that we're given a theory of bosons that disperse in a way like this. And the symmetry, so in what follows, we're going to be assuming that we're working with a system that has translation symmetry. And we're going to be assuming that the bosons involved are conserved. So we have some U1 particle number symmetry. And for simplicity, I said we're going to be working in the continuum and we're going to have great rotational invariance and blah, 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 but that's not so important. So our assumptions going forward is just we have a dispersion with a minimum at non-zero momentum. We have translation symmetry. We have particle number symmetry. And we're going to see what kind of interesting phases we can produce. Yeah. Okay. So let me sketch a very simple example of a Bose Luttinger liquid. In this example, we're just going to be working in 1+1 dimensions, just to kind of give you a flavor of how the construction that I'll be describing later works. And what we're going to do is, as I was just saying, we're going to consider that we're just given some bosonic system that has a dispersion like the form illustrated on this slide. So in what follows, I'm going to be using this KB to denote the Bose momentum, if you like. So the place, the momentum at which the dispersion is minimized. Okay, and so we're gonna start with a system like this, and we're gonna assume here that this R parameter here in a Lagrangian up at the top is negative, so that the system likes to try to become a superfluid. Okay, so it likes to kind of try to condense. Of course, we're working in 1+1 dimensions right now. I'm not going to have any long-range order in a system like this, but we're going to be interested in systems that try to become superfluids. Okay. Now the general, so if you were given a dispersion like this and asked to solve for the IR physics of a problem like this, what you do is you say, okay, well, all the interesting stuff that's going on at low energies is happening near these two Bose points, if you will, the momentum where the dispersion is minimized. And so what we should do if we want to understand the low energy physics of the system is we should break up this field here into a field that kind of lives near this left Bose point, near momentum minus KB, and a field that lives near the right Bose point at near momentum KB plus KB. Okay, so this is the bottom equation in the slide. I'm just gonna, this is what you would do if you wanted to, solve for the low energy physics of a Luttinger liquid or a Fermi liquid in 1+1 dimensions, right? You just break your UV field into, separate out the fast varying component of the momentum from the UV field and look at fields that vary slowly in the IR. Okay, so we just do this. We we decompose this field into these two parts varying at the two Bose points. And you do that, and okay, so what happens is the Lagrangian, when I do the substitution into the Lagrangian, I get a theory for in terms of these left and right fields at the two Bose points. And since I've taken out the quickly varying KB momentum there, these fields just behave as regular quadratically dispersing fields, right? Now I said earlier that I was we wanted to consider a state where the field kind of wanted to try to become a superfluid. So this parameter R in the Lagrangian here was supposed to be negative, right? And if I do that, essentially what happens is that the fluctuations in the amplitude of these fields are not important. They get frozen out. They're massive. And all the action that's going on in the IR comes from the phase degrees of freedom of these fields. So just like what we would do if we were thinking about the XY model or something, or a superfluid, is we write these fields here, alpha is left or right, according to the two Bose points, as just in this phase representation. And then we just write down a effective theory for these phase fields, phi left and phi right. Okay. Now, when we're writing down effective field theory, what we do is I mean, the short way to do this is to just write down the answer using the symmetries of the problem and the low energy field content that you have. So I said that we had boson number conservation as one symmetry, and we also had translation as another symmetry. And when you work out how these symmetries act on these phase fields, well, the U1 particle number conservation symmetry just shift these phase fields by a constant, right? Because this is just how the U1 symmetry acts on the fields. And translation symmetry also shifts the fields by a constant. And this is because the side left and side right, these guys we're living at finite momentum. And so translation acts on the fields in this way. So we just have we know we're just going to be writing down a Lagrangian that is in terms of these phi fields, and we know the symmetry acts on them in this particular way. And so there are not a lot of options for what you can write down for an IR description of this simple system. And so the answer you get looks like this. Oh, sorry. The sort of final IR Lagrangian for this system is just some free bosons for the phase field, and not very interesting, right? I just have these two free bosons, and they can be coupled together in some way with derivative couplings, like I've written in the second line. But there's really not much going on. It's just some free bosons, and these free bosons are acted on in translation, acted on by translation and particle number conservation in some particular way. But other than that, there's nothing much interesting happening. It's just basically free bosons. So what we've done is we've sort of taken our theory with this dispersion. We've essentially done bosonization on it by just looking at the low energy degrees of freedom, and we found 2 low energy degrees of freedom that just disperse freely, and that's it. Okay, now this seems kind of trivial, and it is kind of trivial, but we're going to be using the exact same sort of strategy to think about building more interesting phases in higher dimensions. And the things we're going to be constructing in higher dimensions will be more interesting than just this free action.
Ethan, may I just quickly confirm? Yeah. Does it matter if the left and right boson have different coupling constant eta, or it's just sort of schematic here?
Oh yeah, sure. They can have you can have different coupling constants if you want.
Right. So that's I assume that's not some important thing that I should be.
Yeah, not really. Okay. Let's see. Let me see if I can list all the things that are not important, but that I will be assuming for simplicity. One is this sort of reflection symmetry here. Mm-hmm. So the left and right Bose points don't really have to be the same. They don't have to have the same like velocities or whatever. I don't. There's no rotation invariance since we've been in one dimension so far, but in the coming slides, I'm going to be assuming rotation variance, but that's not important. And the exact, yeah, as long as this, as long as the system is trying to become a superfluid because this R parameter here is negative, then I don't really care about the detail, anything else about the details of the coefficients.
And another thing is, maybe it sounds a little bit weird, but previously let's say in the UV, we do have terms that are single derivative in tau. Now we get rid of that. In the standard way of doing, converting, well, in a condensate, we try to analyze Goldstone mode. There are ways to integrate out density fluctuations to get here, so that it looks relativistic. But you're coming, I guess, according to your explanation, you're just sort of, trying to come up with some effective field theory type description. Yeah. So what would be the direct way to argue that we should not be worrying about single derivative terms?
Right. So indeed. So I'm using these words about effective field theory, and we just write down the answer based on symmetry because I want to be able to like say the majority of the contents of this paper in one talk. So of course, as you were pointing out, what we actually do to write down this a Lagrangian like this is we let me draw some pictures here. So we would write some maybe some rho here,
Uh-huh.
and maybe we would write some rho naught plus d theta, something like this. Keep track of some density fluctuations.
All right.
And then we would integrate out the density fluctuations and so on and so forth. And so you were saying, indeed, we only have a single time derivative in the UV action. And then when we look at density fluctuations, we're going to get some usual Luttinger liquid kind of thing like this.
Yes.
And then plus blah, 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 blah. And then we're going to integrate out these guys, and then we're going to generate some quadratic time derivatives of this. And so, if you want to do this, you can do everything correctly, account for these fluctuations, blah, blah, and then that will tell you, that will tell you this parameter eta here, which is kind of like a Luttinger parameter. That will tell you the expression for this parameter in terms of all the various UV coupling constants and so on. But basically, we know that the IR is only going to involve this phase field, and we can't just write down d tau phi just this, because that's a total derivative and that's not going to do anything. So if you don't want to do any work and are content with not knowing the precise values of the coupling constants and stuff, you can just kind of write down the answer.
Right. Yeah. I mean, I sort of agree with the general philosophy, but if I really add a partial T phi, I'm actually just gonna, it's kind of some funny gauge choice in the time direction. I'm not sure if it does anything, but all right. Yeah, I just want to know.
Yeah, I don't think so. We will have, there are things like this, some Berry phase term where I guess I haven't really talked about. Well, yeah, you do just as what happens when you do normal bosonization. You will have Berry phase terms like this that I'm usually going to ignore because they're not going to be important for what we're going to be doing. Yeah.
Okay. Thanks.
So if you're maybe I might have sort of tacitly been assuming that everyone is familiar with bosonizing, or at least bosonizing bosons here. But yeah, if you're familiar with bosonization, we're essentially just bosonizing bosons, except the bosons we're bosonizing have this funny dispersion in the UV. And yeah, not much more than that yet. Okay, so now we're gonna try to do something essentially the same thing, except we're gonna try to do it in 2 dimensions. Okay, and then 3 dimensions, 4 dimensions, 5 dimensions. It's all the same after this. Right? So we're gonna consider. So we're just gonna assume that we have some system of bosons that has again has a dispersion with a minimum at some non-zero momentum. So I hope this picture is clear. We again have some momentum, some Bose momentum here, where the dispersion is degenerate. And yeah, we have some system of bosons. We're again going to assume that they want to try to become a superfluid, and we're going to analyze the IR properties of a system like this. Okay, so what should we do? Or we're just going to follow the logic of the previous discussion. So what we're going to do is we're going to break up this low energy annulus around the Bose momentum. Maybe I should draw it here. We're gonna we take this region here of kind of the low energy field, the fields that live at momentum with low energies, and we're gonna just kind of focus on the stuff that's going on down here, and try to write down an effective action for this stuff. Okay, so the way we're gonna do that is, just like in 1 dimension, how I took my UV field and I broke it up in terms of a field that lives here and a field that lives here. We're going to do the same thing, except I'm just going to now take this picture and kind of like rotate it in 2 dimensions, right? And so this is, I'm attempting to illustrate here in this figure. So in this figure, this is kind of like a section of that annulus. And what we're going to do is we're going to break up this annulus into like a bunch of small chunks. And then we're going to define fields that have momenta supported on each of these chunks. And we're going to work with those fields. So this decomposition is illustrated on the left half of the slide here. So my UV field psi, I kind of like separate out the quickly varying part of the momentum at each angle on this low energy annulus. And I deal with fields that are kind of varying slowly with respect to that momentum. So here, I'm going to use this gamma index to denote sort of an angle along along this surface. Okay. So, and then
sorry to interrupt. Sorry to interrupt.
Go ahead. Go ahead.
So you need a degenerate surface of local minima of the boson dispersion. Is that right?
Yeah. So maybe go ahead with what you're.
Yeah.
If you're going to say anything else.
So you mentioned that rotation symmetry is not important.
Yeah. Good.
But it seems to me like you need some sort of a continuous symmetry in order to have a degenerate surface.
Yeah. Very good. Yeah. So you could complain that like we're doing condensed matter physics and there's always a lattice and we're always going to have some anisotropic dispersion or something, right? And so indeed, so the point of view that we're going to take here is we're going to assume that everything is nice and idyllic and we have rotational invariance. And then after we kind of come up with the right IR description for a phase like this, we're going to examine, well, I guess I won't do that in this talk, but you can examine the extent to which perturbations that break the perturbations that break rotational symmetry are relevant or irrelevant. And you can show that perturbations which change your dispersions to be not rotationally invariant are irrelevant in the RG sense. So
but if you were to start with a 2D boson dispersion that had 4 local minima instead of a continuous surface of them,
yeah,
right, then you would not end up with the phase you're looking for.
I think the claim is that you would, but it's a question of just these terms being irrelevant or relevant, right? So the claim is that all I'll make a statement about is that infinitesimal, an infinite, just like any RG analysis is just a stability analysis about like a infinitesimal perturbations about some fixed point. All I'm going to say is that infinitesimal rotational symmetry breaking perturbations are not going to be important.
Got it.
Actually,
but
Oh, sorry. Yeah, I was going to sort of elaborate a little bit more on this, or extend the question a little bit. So I can see that presumably there's some interaction-driven symmetry breaking term that are irrelevant. But if I just literally turn on some quadratic stuff, that would not be irrelevant, right? That would be just strictly marginal. I mean, we could use that to just make the system observational in the area.
You mean like
I changed the dispersion by hand, basically. That I think that's what Sam is asking about. We just we could change everything at the quadratic level, and then it's hard to argue those things are going to be irrelevant, right? I mean, I can keep the entire model like non-interactive.
Right. So usually what you would do is you would usually this would be true because usually you kind of like do the way we approach RG and the way we do scaling is kind of like done to keep any kind of free term invariant or exactly marginal by kind of construction of the way we do the scaling, right? But the way that the natural way to do scaling in this system is to define the RG by kind of just only scaling in this direction as you would in a Fermi liquid kind of. So the way that RG happens is by like eliminating modes as by depending on how far away they are from this Bose momentum here.
Yeah.
So kind of like if you consider a perturbation which changes the dispersion by like, this is going to be sort of hard to draw, but say like you change the dispersion so that like the dispersion in this direction tangential to the Bose surface is kind of like not flat. Like you add some well, I have a figure on a later slide that kind of gives a better example, but you just like we were talking, maybe you have like there are only 4 minima to this dispersion here, and then it's like kind of like slightly not minima at other points, right? Yeah, essentially these like perturbations to the dispersion don't affect correlation functions in the IR, provided that you start from a state that provided that you do this kind of like renormalization group approach where you start from a uniform state. So yeah, so maybe to summarize this kind of convoluted answer that I've been giving is if we assume rotational invariance, we go to the IR and then we look at the effect of rotation breaking perturbations to the dispersion in the IR, they don't affect any correlation functions for weak enough perturbations.
Okay, fair enough. So and that includes interaction or quadratic terms, everything. That's I just want
yeah, that's right. Yeah.
Okay.
Yeah, the special thing here is just that, you know, just adding yeah, maybe you'll get a better sense of how this works in the coming sections. But essentially, because the dispersion is kind of funky, the way in which you set up the RG is a little bit different, and then that means that the way in which free perturbations to the action are dealt with is also slightly different. Yeah.
Okay.
Okay. Yeah. So we're going to be doing this. We're going to be breaking up this surface into these patches like this. You know, we'll be taking this limit over here where we think about a large number of small patches, right? When we go to the IR, we're just going to be looking at a very thin annulus about this low energy momentum here. And okay, then the dispersion here, well, okay. sorry, this depends. I think I wrote this slide when I was considering a relativistic limit. Let's add a squared here. It's just going to be a quadratic dispersion along each point on this annulus. Okay, and so the reason why we do this is because the fields at a given kind of patch on this annulus here only disperse along one direction, right? So if we kind of if we ignore the fact that well, if we just break it up this up into discrete chunks like this, and we assume the dispersion doesn't really change too much within each chunk, then a field living on this chunk only disperses in this k parallel direction, and it doesn't have any dispersion along the perpendicular direction, which means that a field that lives on this patch, this guy, is sort of going to behave in a quasi one-dimensional, 1 + 1 dimensional fashion in the way that it fluctuates, and this will allow us to take advantage of, you know, all of our knowledge about 1 + 1 dimensional physics to kind of ask what happens to this system. Okay, so I guess I anticipated myself here. So as I was just saying, we have this disperses in one field, and because we're interested in states that are trying to become superfluids, we're going to use this. We're going to again, you know, if the fields are trying to become superfluids, the radial modes here that I haven't written are going to be frozen out. You know, there'll be density fluctuations like what we were discussing earlier, right? But for now, let me, following the same kind of line of reasoning, let me ignore these for now and just focus on the.
Oh, sorry. Yeah. Also, there is a pretty strong assumption that rho is the same for every gamma. Is that what
yes? That's a strong assumption. That this is my crucial assumption that I will discuss in a few seconds.
Oh, okay. You're going to talk about. Okay, sorry. We should wait.
Yeah. No, that'll be very important. So, yeah, we assume some uniform amplitude ordering like this, and we just focus on these phase modes. Now, as in the 1D example, right? We want to know the way in which these phase modes transform under the symmetries that we're assuming. We have particle number symmetry, which is just shifting these modes by a constant, right? And then we have translation symmetry. So if I translate through a vector mu, these fields, since we're living at finite momentum, they transform with some shift in this way. Okay, now as Xiaoming was just saying, yeah.
Sorry to interrupt. So if you're going to address this later on, you don't have to talk about this now. But I was just wondering if you define this problem on the lattice, and let's say you're working with some commensurate density, can I tune a bandwidth tune transition from this liquid to a Mott insulator?
I don't know. I don't know. Transitions out of this liquid into other things are, well, I don't know. There are a few ways that we thought about doing it, and they all kind of got us confused for at some point or another. So let me just say that I don't know, and if more intelligent comments come to me later, I'll let you know.
I mean, but morally, I don't see anything wrong with trying to tune a superfluid to Mott transition. I just don't. Okay, so I guess the question was, have you thought about how to lose this Bose surface continuously?
Yeah, so you can think. We have thought about trying to lose this Bose surface continuously, and you can try to think about doing some kind of vortex condensation kind of deal that's going on, right? The issue is that vortices are a little bit tricky in this system. So yeah, so normally you want to condense some kind of vortex. You can ask whether the right kind of vortices to be condensing are like vortices in these phase fields here, or like vortices in the phase of the original UV field, like not these patch fields, right? But like the original UV field, right? And I don't think, if you want to try to condense vortices to get some kind of insulating phase, then you don't really want to be condensing vortices in these objects. The vortices in these fields are a little bit weird to work with, and I think don't really make good sense on energetic grounds. But if you're trying to describe vortices in just this UV field here, then they're a little bit awkward to describe in terms of the low energy degrees of freedom, just because the natural way of understanding what's going on in the IR is to do this kind of decomposition to a bunch of patch fields. So I don't see anything wrong in principle with doing some kind of vortex condensation like this, but well, probably if you want to attack this problem, the variables that I use to describe the IR might not be the most useful ones to employ.
I see. Okay, thanks.
But yes, but very, very interesting question, and we tried to see if we could have anything intelligent to say about this, and we didn't really make a lot of progress. But we didn't try very hard. This was just like something that we're thinking, maybe we may not want to discuss. But I think definitely you're probably well equipped to answer a question like this.
Sorry, I'd like to ask maybe a sort of a stupid question. You said that each of the modes along the annulus is like a pseudo 1+1D, because there's no dispersion in the perpendicular direction. I'm just sort of confused on that point, because like if we say that the low energy modes are forming an annulus, doesn't that mean that one actually should be able to get to a neighboring mode with a zero energy perturbation to the field?
Yeah. So are you're saying kind of like
a Goldstone boson, right?
Yeah. Goldstone, but well, maybe can I ask if so one thing you could say is the way, if I say these are just 1+1 dimensional, 1+1 dispersing kind of guys, there's no difference between some kind of circular minima that I assumed and just some kind of like giant where's my, oh no, my iPad, my pencil has 0 battery. Okay, bear with it. So there's a difference between having like an annulus and just like a straight line, right? And if I just linearize the dispersion and I say it's just one dimensional, then there's no difference between just having a big straight line, right? So the kind of curved nature of the annulus does show up, and it shows up sort of in this transformation law here for the way the fields shift under the symmetry, under translation symmetry. That this is one place in which this curvature kind of shows up. And that'll be important for determining like what kinds of interactions we can write down. I haven't really gotten to this, but there will be various sort of instabilities that you have to worry about in phases like this, and the sorts of symmetry allowed interactions that you can consider will be determined by the geometry of this Bose surface by virtue of you need to conserve momentum and stuff when you're writing down perturbations, and that affects the things you can write down. So the short answer is that this curvature does affect things, but in the present discussion, in terms of the formulas I've written down so far, you're indeed correct that it hasn't played a role yet.
Okay, okay, thanks.
Okay, so now let me get to this crucial assumption that Changming was talking about. So what we're going to be assuming is that the amplitude modes here of these fields are massive, first of all, and that their expectation value is the same at every point on the Bose surface. So we're going to be assuming that there's no spontaneous breaking of rotation symmetry. Right? You could imagine that maybe what would happen is that the system instead prefers to break the symmetry, and I have my degenerate annulus, where I have the dispersion is degenerate, but then like all of my bosons tend to like go into just this patch, or maybe they go into these two patches or something, right? And we're going to assume that doesn't happen. Now, whether or not something like this happens, whether or not you try to spontaneously break symmetry, is a question of sort of UV details, in that I haven't really talked about what's going on in the UV other than the dispersion, but we have this side of the 4 term. Of course, there's a other big mess of stuff, and this big mess of stuff can include various rotation breaking terms and all this crap, right? And for some choices of this kind of crap over here, you will indeed favor some rotation symmetry breaking phase like this, where you try to like put all of the modes into one wave vector. But there are other choices of the UV interaction for which there's no obvious minimizing the exact free energy for all possible kind of terms you could add, and trying to figure out exactly which ones kind of frustrate this spontaneous symmetry breaking and stuff is kind of a difficult task. But there are some interactions for which it appears that a rotation invariant phase is stabilized, and depending on I might not get to it, but there are actually examples of in experiment where there are some kind of interesting magnetic systems where we see empirically that you have a large number of low energy degrees of freedom along like a sphere in momentum space to a good approximation. So there seem to be some examples in reality where this crucial assumption here is satisfied. And there seems to be some theoretical models that you can kind of cook up such that this assumption is satisfied. But this is just a matter of UV details, and it's for any given kind of context that you want to consider, this assumption may or may not hold. But we're going to be making it in what follows. Okay, so I hope that's clear. Okay, so now we're going to write down again. There's kind of if we want to do things rigorously, we're going to do another kind of bosonization thing, and we're going to have density fluctuations, and we're going to integrate them out, blah, 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 blah. But for the purposes of the present discussion, we're just going to, realize that we have some symmetries and we have some symmetry action on the IR fields, and we're just going to write down the simplest kind of IR action consistent with the symmetries. And so we get something like this. It's kind of just the obvious generalization of the 1 + 1 dimensional story I was telling you about. Again, gamma is an angle running over this Bose surface, and phi gamma is the phase mode that lives on at that angle. And here, so we have some free action for these fields, nothing interesting here. And we also have some couplings at different points on the Bose surface between fields at different points. And these are like Landau parameters, if you from from Fermi liquid theory. And we also have this some coefficient eta here, which in Fermi liquids is fixed, but here in the present context, this sort of Luttinger liquid parameter here can have any value. And this fixed point described by this this theory is what we're calling a Bose-Luttinger liquid. So it's basically just an infinite number of free bosons coupled together in this way. Okay. Now, before I talk about whether or not this kind of description here that I've written down is robust with respect to interactions and all this other stuff, let me just give you kind of like a highlight of the phenomenology of a phase like this. So this phase is kind of like Fermi liquids in some aspects, but not like Fermi liquids in other important ones. So, okay, I mean, you can just read this, right? So Fermi liquids, the stuff that's like Fermi liquids, we have like a compressibility, as it relates to the lambda parameters. We have a linear and T-specific heat. Correlation functions oscillate at this momentum KB. This system turns out to be a metal, and it has metallic conductivity. There's also a large IR symmetry group, like in Fermi liquids, that I had kind of mentioned at the beginning. The boson number at each point on the surface is conserved, right? And so in this sense, this phase that I wrote down is kind of similar to a Fermi liquid, but there are some important differences. So there's no Bose C here, right? So there's not going to be any kind of Luttinger's theorem or anything like that. There's no chirality, right? There's no inside of this Bose surface. There's no outside, right? So there's no, unlike the Fermi liquid, there's no chirality. I guess I won't have time to talk about it, but the RG flows in a system like this are very different from a Fermi liquid. And because we have this Luttinger parameter here, this eta, which can be anything, any real number, any positive real number, correlation functions in these phases have continuously varying exponents, right? So just so just like, you know, we're familiar in one plus one dimensions of various types of phases that have continuously varying exponents, and by kind of stapling a bunch of 1 plus 1 dimensional phases together in this way that I've described, you can also get some examples in 2 dimensions where you have these continuously varying exponents.
Ethan, are there analogs of 2kF type singularities, meaning something at 2 kb?
Yeah, let me yeah, there are.
Oh, okay, that's what you meant. Sorry. Okay.
Yeah. There's like the analog of like the Kahn anomaly. Basically, the phenomenology is essentially Fermi liquid phenomenology, except all exponents are now continuously variable, essentially.
But if I may just ask one more question. So if I look at the full Q and omega dependent density response and compare that to a Fermi liquid, is there, I guess I missed this, is there an analog of a particle hole type continuum here? I mean, I see the collective modes, and you're saying there are features near 2 kb, but what does the rest look like?
Yeah, let's see. So I mean, if I were to go ahead.
Yeah, if I were to rephrase my question as, suppose if I'm an experimentalist and I don't know if I'm probing a system which is a Bose-Luttinger liquid versus some crazy electronic non-Fermi liquid, and I come in and I do some kind of scattering experiment and I do density response, Q and omega. So what is different for the Bose-Luttinger liquid?
Yeah, well, I'm not sure if there are. I mean, yeah, maybe I can just say what I know, and then maybe help me answer the question. So, you know, the correlation functions that you compute, that you compute in the space. So let's compute the correlation function of the bosons, the UV bosons at k omega, right? So you can just work out exactly what this correlation function is, because it's just a bunch of free bosons, and you get something that looks yeah, I don't know how helpful it is, but it's basically just like the Fermi liquid result, except the exponents that appear in the correlation functions are placed with like with non-universal numbers. So in the sense that
Right.
a non-Fermi liquid, a fermionic non-Fermi liquid, can give you arbitrary exponents in the correlation functions you look at, then just looking at correlation functions, I guess, would not tell you.
Right. But now I guess my question is about the two-particle response.
Yeah, I think it's the same. I mean,
but how should I be thinking about the analog of the particle hole continuum? I mean, the Bose-Luttinger liquid doesn't have, or does it? Like, I guess I can think in terms of particle hole excitations near the Bose surface, or
well, I guess it's kind of I mean, there aren't really any holes, right?
right. So then I guess that's the key difference. There is no particle hole continuum for a Bose-Luttinger liquid. So if
yeah, there are definitely no holes, but in terms of like what the response functions look like as a function of Q and omega.
Okay, I don't need to take up more of your time. We should have a separate conversation, I think, about this.
Maybe may I just maybe may I just make a very quick comment? If it's unrelated, then we can discuss that. But the way that we end up having this 5-field propagator, it's coming out of integrate out of density fluctuations, right? So if we just say, in a way that these 5-field fluctuation is like kind of conjugate to the density fluctuation, then does that sort of partially answer the Banjan's question? I mean, it may not be literally particle hole continuum, but it's some density fluctuation that we're working with.
Yeah, indeed. I mean,
it's not a continuum; it's probably linear. It's a
well, it can kind of get messed up because when we're considering correlation functions of the UV field, the UV field is like a sum of a bunch of things at all points on this boson on the surface, right?
Right. Yeah, I'm just saying that for every gamma, there is no continuum. I guess that's what I'm trying to say.
Yeah. I mean, it's kind of like we can bosonize Fermi liquids too, right? Like it's a legitimate thing is to if you want to talk about like the particle hole continuum and the response functions and blah 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 in the Fermi liquid, you can compute all of these things by bosonizing the Fermi liquid and working in terms of phase modes and stuff like this,
right?
Which is essentially what I'm doing, right? Because bosonizing fermions and bosonizing bosons in a lot of sense are very similar things, right? But when you bosonize bosons, you can have you kind of have more options, right? You're not constrained by things like Luttinger's theorem, and you're not you don't have chirality, and so the correlation functions are a little bit different in that sense. But
yes,
right.
Yeah. So, but certainly any kind of quantities that you're interested in, if I'm not able to explain them adequately right now, they can be calculated easily because it's a free system. Okay, so in the interest of time, I'm just going to kind of like say maybe in words what's going on in the rest of my talk. So there are a few important things to address that I haven't gotten to yet, right? So all I've done so far is basically just write down in Lagrangian without, I mean, anyone can write down a Lagrangian like this, right? But in order for it to be interesting, we need this Bose surface thing that we constructed to be stable with respect to perturbations, right? If it's not stable, then it's some very, very fine-tuned system and it's not interesting, right? So yeah, as in Fermi liquids, right? One reason why a lot of the interactions in Fermi liquids are irrelevant is coming from kinematic constraints that come from momentum conservation, right? That really limits this kind of scattering processes that you can consider. And as in the Fermi liquid, that's true in this case as well. But unlike the Fermi liquid, right, we have these continuously varying exponents. And so that will change sort of the conclusions we make about the IR, about the relevance or irrelevance of various terms. And yeah, so I'll just say that the most important kind of perturbation to think about, like in Fermi liquids, in this case, is a BCS interaction. So this is, exactly what it is in Fermi liquids. You destroy two bosons here, and then you create two bosons over at some other point, right? And when you represent a process like this in the IR variables, it becomes some kind of cosine thing here. So yeah, you can see this is just the IR representation of this guy. And okay, so you have to figure out what the dimension of this operator is in the RG sense. And I won't tell you exactly how that's done in the interest of time, but I'll just tell you the result, which is kind of interesting. The result is this. So the dimension of this operator is determined by this kind of Luttinger parameter eta. What this means is that if you recall in Fermi liquids, the BCS instability was always marginal, and whether it was relevant or irrelevant was determined by higher order terms. In the present case, that's not true, and the BCS interaction may either be relevant or irrelevant depending on the value of the Luttinger parameter. In particular, you can choose the Luttinger parameter such that it's irrelevant, and then you can show that all other interactions that you could add are also irrelevant. So essentially, you can show that this phase I wrote down on the few slides ago is stable. Let me just mention that one interesting thing here is that that we haven't explored yet, but I think would be super interesting, is that the fact that you can continuously tune the scaling dimension of this interaction, of the most important interaction here, right? What this means is that you can get a beta function for this BCS coupling. I guess I called it G dt, which looks like maybe some small positive number here times G minus, if you compute the second order correction, you find minus G squared, plus times something plus blah 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 blah. Anyway, this you can then engineer it to get a fixed point here at non-zero coupling. Mm-hmm. So there exists some phase here which is not free, but is also, so it's interaction because you have a non-zero coupling, you have non-zero interaction here, but it's also, you can make this RG flow from zero coupling to the fixed point described by this function arbitrarily short. So I guess there's some interacting phase here that can be accessed perturbatively that might be kind of interesting that we haven't looked at yet. Yeah, so that's something that would be cool to do for the future. Let me skip that. Yeah, I guess I've already gone over, but okay, you can ask if you want to ask about how something like this might be realized in experiments. We can come back to the slide, and I'll just let me just throw out this, and then I'll end.
All right, let me represent everybody to thank Ethan for the wonderful talk, and yeah, we are open for questions.
Can I ask a question?
Go ahead, of course.
Sorry, Ethan. I would like to know something about manganese silicide. If you could just talk about it briefly.
Yeah. So, okay, great, thank you. So what happens here is
I should say this was not a planted question. I'm genuinely interested.
Yeah, great. Okay, that makes me feel good. It also gives me a chance to refer to this figure that I had mentioned earlier. This is so okay. So what the system is it's a helical magnetic system. So it can be described by some kind of I just probably write free energy here, but some free energy in terms of some magnetization vector m, and this is the Jelsinski-Moria. I don't know how to pronounce this. The DM term you can get in inversions and breaking magnets. That appears, curl magnetization dot B is this. This is going to generate your magnetic field that you couple with to the magnetization. And you can imagine that when you look at this, just when you diagonalize this free energy here, right? We've got some kind of Q squared, M squared kind of thing here. And then we have some kind of QM thing over here. And so what happens is that when you diagonalize this guy, you see that there's a minimum well, this is in 3 dimensions. Let me just refer to this figure. You get a minimum in this dispersion along some sphere in momentum space. So just by if I just restrict my attention to this free energy here, you would conclude that the magnetization in the system has a preferred magnitude of, i.e., prefers to order at a wave vector which is non-zero in magnitude, but which does not have a preferred direction. At least if I only focus on these terms. And so, yeah, what's seen in an experiment is that you have some kind of like a large spectral weight kind of almost uniformly distributed along a sphere momentum space, which is one. Okay, this is one of the motivations for leading to considering weird systems like this.
Ethan, I missed this. I don't know enough about this compound. So the LM is just the magnetic. I mean, is the system then doped with electrons that turns it into the metallic non-Fermi liquid, or what's going on? Like,
yeah, usually people are applying pressure. This
okay.
tension is pressure. Yeah.
And P equal to 0 is the insulator, just with some magnetic texture.
Ferromagnetic metal, I believe.
Okay.
Yeah.
And
we essentially in this problem we have a Fermi liquid with some magnetization textures going on that look like something like this, and then as this as you change this parameter here, you go from something where the magnetization is not doing anything interesting to something where the magnetization is kind of like trying to sort of spread out and smear itself along over the surface of the sphere. And yeah, so what happens is that what's observed in the system is that when the magnetic moments start trying to like smear themselves out over this sphere, you get some weird transport stuff. Well, the people measure the resistivity in the system, and they get this power law down here, which is a little bit interesting, right? And I think so far there's not like a super good understanding of where exactly what's going on with the magnetic moments and how they're interacting with the electrons to produce some kind of power law like this. And so anyway, with our idea in this context is saying that, look, we have these we have this kind of we have this boson, this magnetization guy that wants to live over on the surface of the sphere. So let's see what happens when we take a system like this, a Bose-Luttinger liquid like I was describing, and we couple it to a Fermi liquid essentially, and we just see what the boson part of this theory does to the electrons. And okay, the calculation that we did told us that the resistivity in a system like this, where I couple this Bose surface thing to the electrons, just like with most other things in the system, the exponents is continuous, and the resistivity depends on this temperature to this Luttinger liquid parameter. Of course, okay, so in what I've been discussing, this Luttinger liquid parameter is determined by some UV stuff that we have no control over. It's some non-universal thing. So maybe the fact that we see this exact 3/2 exponent in experiment is a little bit weird or unnatural from the point of view that I've been discussing. But at least a system like this gives you motivation to kind of consider the sort of bosonic systems that I've been talking about.
And the coupling between the Fermi liquid to the BLL, is that density, or it's just some boson coupled to fermion density via Yukawa?
Something like this.
Okay.
Yeah.
All right, thanks.
Yeah. So the problem is just Fermi liquid, and then you have the magnetization with coupling to the fermions, and then you integrate out this guy. You integrate out like the Bose surface sort of, and then you see what happens.
Thanks.
Okay. I think we are I still have a couple of questions, but I think it's best that I call it the the end of the official session now, and
Yeah.
people have other things to do, or they wanted to leave or need to leave, they can feel free to do so. But or if you have more questions, please just unmute yourself and ask. Okay, I do have a question. Well, actually two. One is technical. The other is, well, okay, slightly, maybe a bit ambiguous.
Mhm.
But if I'm just, putting a hat of an effective field theorist on,
Mhm.
I noticed that in your Bose surface formulation,
Mhm.
there is always this nabla gamma combined with phi gamma.
Yeah.
You never have a situation with nabla gamma prime acting on
Right.
phi gamma. Is that something that I can get directly from symmetry grounds, or it's really something that is more microscopic than symmetry-based analysis?
Yeah, essentially. So, I mean, it essentially just comes from by virtue of the fact that, we did this, this is working in the, a little bit subtle here. These are kind of like issues that we agonized over for a long time, but essentially what we're doing, right, is we took this thing and we broke it up into all these surfaces, right?
Yeah.
And what happens is that you can show that when you do RG and you flow to the IR and stuff like this, you're not generating like anisotropies in this dispersion where like maybe you do something like you're not going to generate stuff like this, right? So the dispersion for these fields is they're going to continue to only disperse in this direction.
I see.
So this essentially just comes from the consequence of that, like I was saying, these fields are quasi 1D, 1 plus 1D, right? Now the exact extent to which you can treat them as 1 plus 1 dimensions, like do you really want to have like the literal limit where these patches are like infinitesimally thin, or do you want to like consider some finite thickness, in which case the dispersion like varies a little bit, and all these details, right? I mean, these kind of details are kind of like, you kind of know at some high level that they can't really matter, because this procedure of breaking up the surface into a bunch of patches is kind of like just a artificial thing that we do to be able to compute things, right?
Yeah.
But you still have to kind of like obsess over these kind of technical issues to convince you. Well, at least this was what I had to do to convince myself that something like this is legitimate. So yeah.
I see. Yeah, and maybe I should stop recording.